Okay, problem 3. I'm having good luck with the whole copy and paste thing today, so let's hope that holds out. We've got an object, this little ball on a string, whatever, released from rest over here on the left side, and it swoops down, and it has some speed here. So I want to find v. I'm going to go ahead and label my state. So I'm going to call this 1, 2. So I want to find v2, which is its speed there, and then it's going to keep arcing up, all still in a circle, until it reaches here, which I'm going to call 3, and I want to find this also, which I'm going to call v3. And this is part A is asking for v2, and part B is asking for v3. v1, of course, is equal to 0. Okay, so I'm just going to do this, and let's do state 1, kinetic energy equals 0. I need to find some reference point for my potential energy. So I guess what I'm going to do, I don't know, I'm feeling saucy today. So I'm going to say my potential energy due to gravity equals 0, right, at this point. Okay, so I'm going to say at this beginning thing, potential energy to gravity equals 0, which means mechanical energy also equals 0. Well, that's convenient. Okay, at 2, my kinetic energy equals something. Okay. Well, actually, no, what I'm going to say is, I've already defined V2 there, so I'm going to say it's 1/2 mv2 squared, and potential energy due to gravity there is going to be, it's below my 0 potential energy point, right? So my potential energy here will be negative, and the string length is L. That's the distance down it's going to be from vertical, so this is going to be negative mgl, and then Emec there, of course, is just going to be 1/2 mv2 squared minus mgl. At state 3, we're going to have we'll tell you what, let's do part A since we've got enough to do that. So the key fact here is the mechanical energy is conserved. The only force changing energy here, or the only force that's doing work at all, is gravity, and we're handling that with the potential energy. There is the tension force in the string, but as we always have with these strings, things moving on strings and ropes and cables and all, the direction it's going at any point is perpendicular to the tension in the string. So right here, it's going this direction. Tension in the string's pointing that way, so it's right angle. So that's not doing any work. So what we can do then is do this conservation of mechanical energy. So we say right here, we take mechanical energy at 1 is equal to mechanical energy. Yeah. Wow, I can't talk. Mechanical energy at 1 equals mechanical energy at 2. So 0 equals 1/2 mv2 squared minus mgl, which then we cancel out the m. We get v2 squared equals 2gl. Okay, so let us go and see how that works out. So was it speed when it reaches its lowest point? It's going to be square root of 2 times g times l. So square root of 2 times 9.81, and L we said was 120 centimeters, which is 1.20 meters, and it's going to be moving 4.85 meters per second. 4.85, and boom, nice. Okay, so, and then what's its speed when it reaches its highest point after the string catches in the peg, which, as I said, after you go all the way around, it's up here. So right here. So let's do for part C, 3. Kinetic energy at that point is going to be 1/2 mv3 squared, where I said v3 is its speed here. Potential energy due to gravity is going to be, now this is tricky because we have this, how far down is this from the 0 point? Well, it's D takes you down to this peg here, right? But then it's R back up. So this is going to be negative mg times D minus R. And we'll recall that R equals big L minus D. So let's see, D minus R equals D minus big L plus D. So this is actually going to be, well, it's going to equal, let's see, this is going to be 2D minus L. And then write negative of d minus r, because if it's negative here, wait a minute, so this is 2d minus L, so then negative of d minus r is going to equal L minus 2d. So, long story short, this is going to equal mg times L minus 2d. Wow, that was way more effort than was worth, wasn't it? Okay, and then, so E mech here, mechanical energy, is going to equal 1/2 mv3 squared plus mg times capital L minus 2d. So now we can set this. Mechanical energy is conserved from here to here, remember, and it's conserved from here to here. But that means it's also conserved from here all the way through to here. So all three of these mechanical energies are equal. So we can set this equal to whatever we want, either at 2 mechanical energy or 1 mechanical energy. And I think it's obvious it's going to be a lot easier if we set it equal to mechanical energy at 1. So let's do, because that's just 0, so let's do that and this. And what we'll get here is 0 equals 1/2 mv3 squared plus mg times L minus 2d. I hope I'm not getting out of range there. And then that means we cancel out the m and multiply by 2. We get v3 squared equals mg, or 2mg, times 2d minus L. So that's, wow, that's kind of an annoying expression, but could be worse. So let's go ahead and plug that in. Let's do square root of, let's see, 2, actually, sorry, we had a, my bad, we canceled out this m, so this m is actually gone. So, sorry, the m should be out. 2g times, that's a little better. Okay, so 2 times 9.81 times parentheses, and then we'll close that. So in here is where we're going to put our 2d minus L, 2 times d minus L. So let's see what these are actually. 2 times d minus L. D is 72 centimeters, so 0.72 meters, and L was 1.20 meters. So there we go, and that's going to be our velocity, our speed when we get to the top of this arc up here. It's going to be 2.17 meters per second. So let's see if I'm correct about that. Yes, I am. It's a good day to be me.